All right, let's dive into the secret life and death of something that's probably in your hand or pocket right this second, the battery. It's not just some magic box that holds power. It's actually a chemical story with a beginning, a middle, and, believe it or not, a very predictable end.
We've all been there, right? You see that dreaded 1% warning just when you're about to take a picture or call for a ride. It feels so random, almost like a personal attack. But it's not random at all. What's actually going on inside that little rectangle is a totally predictable and honestly, a pretty fascinating story of chemical destiny.
So, at its core, a battery is not magic. It's basically a self-contained chemical reaction. It's a tiny power plant in your pocket. And that force pushing all the energy out, the thing that makes your phone light up, is called voltage. But where does that initial push even come from in a brand new battery?
To really get what voltage is, we have to shrink down, like way down to the atomic level. I want you to imagine a microscopic tug of war. You've got all these different chemical elements, and they are all fighting over just one thing, electrons. And the intensity of that fight is what creates the power. In chemistry, we actually have a way to measure this pulling power. It's called the Standard Electrode Potential, or E0 for short. The easiest way to think of it is like a power ranking for elements. A really high positive number means an element is just desperate to grab electrons. On the flip side, a big negative number means it's super happy to just give its electrons away. And just look at the difference here. It's huge. You've got fluorine way up at the top. It is the undisputed champion of grabbing electrons. And then way down at the bottom, you have lithium, which is practically throwing its electrons at anyone who will take them. This massive difference, this mismatch, that is the secret sauce for a powerful battery.
So to build a battery, you just put these two opposites together. You take an electron grabber, your fluorine, and an electron giver, your lithium. The bigger the gap between their pulling power, the stronger the voltage you're going to get. It's that fundamental chemical imbalance that creates all the energy.
Okay, but those power rankings, they're for perfect, ideal lab conditions. In the real world, inside a battery that's actually working, things are constantly changing. And that constant change is the real key to understanding why it has to die eventually. Let's see how. So what happens when you actually use it? You turn your phone on, and those electrons finally start to flow from one side to the other. Well, that's when the beautiful, stable chemistry inside the battery starts to change. And that perfect starting voltage, it begins its long, slow journey downwards. And this is the rule book for that journey. It's called the Nernst Equation. Now, don't let the letters scare you. All you really need to know is that this first part, E0, that's the battery's perfect, out-of-the-box voltage. But this whole second part here gets subtracted from it as the chemicals get used up. This is the math that proves why your battery life always goes down and never up. Okay, so here's what's happening. Think of a fresh battery as having all of its fuel, we'll call them reactants, on one side. As you use your device, that fuel gets burned and turned into exhaust. We'll call that the products. And the more exhaust builds up, the weaker the chemical reaction gets. The Nernst equation is just tracking this process, and it shows that the voltage can really only go one way, down. Which, of course, brings us to the final act in our battery's life. This chemical reaction can't just go on forever. Sooner or later, it runs out of steam and hits a wall. This is the point of no return. As more and more of that original fuel gets converted into exhaust, that chemical push gets weaker and weaker. That tug of war we talked about, it's not much of a battle anymore. It's more like a stalemate. The whole system is just winding down, getting closer and closer to a state of perfect and totally useless balance. And then it happens. The voltage hits zero. This isn't just a low battery anymore. This is chemical equilibrium. The tug of war is officially a tie. There's no longer any net push of electrons in either direction. The battery is, for all intents and purposes, flat. So why is 0 volts the absolute end of the line? Well, it comes down to a concept called Gibbs free energy. It's really just a fancy term for how much useful work you can get out of a system. And as you can see from this equation, it is directly tied to the battery's voltage. It's a really simple but powerful connection. If the cell voltage, E cell, is 0, then the Gibbs free energy, delta G, is also 0. It means the battery has 0 capacity left to do any useful work. It has reached that perfect chemical balance. And from an energy point of view, it's dead. So we know the chemical potential is dropping, but at the exact same time, there's another kind of struggle happening inside the battery. And it's all about the physical journey the ions have to take to complete the circuit. So you've got two different ways electricity is moving here.
Outside the battery, in the metal wires of your charger and your phone, you have what's called metallic conductance. That's the normal flow of electrons we all think about. But inside the battery, it's different. It's called electrolytic conductance, and it's the movement of whole atoms, ions, through that liquidy gel-like solution. You need both to be working for your battery to function.
And you know, just like swimming in water is a whole lot different than swimming in honey, there are tons of things that can slow down those ions. The stickiness of the chemical goo inside, how big the ions are, even the temperature, it all adds up to create internal resistance, which absolutely affects the battery's performance.
So let's just recap that whole journey really quickly. It all starts with a powerful chemical imbalance, creating a high initial voltage. Then, as the battery works, that chemistry changes, which causes the voltage to drop, a process the Nernst equation describes perfectly. And finally, the system hits equilibrium. Voltage drops to zero, and the battery just can't do any more work.
So it feels like a sudden, annoying failure is actually the totally predictable end of a chemical story. It's a journey that starts with an intense atomic tug-of-war and ends in a perfectly balanced and perfectly powerless state of equilibrium.
So think about this. If a dead battery is just a system in perfect chemical balance, what in the world are we doing when we plug it in to recharge? What kind of force is strong enough to literally pull a system out of equilibrium and rewind its chemical clock? Well, that sounds like a story for another explainer. Thanks for watching.